Good. So today we're going to talk about character tables and reducible and irreducible representation. And so this is exciting for the folks that came up through our program because this is new information. I did not do this at the undergraduate level. And so sharpen your pencils. So what is the character table? Well, it's really the Rosetta Stone for converting molecular motions and molecular orbitals and everything to the spectroscopic phenomenon. Okay. And so you've got these character tables in your hands. You can look at them. What do you see on the top left-hand corner of every one of the character tables?
The point group.
The point group, yeah. So that's important. If you don't have the point group right, you won't have the right character table. And you won't get the point group right if you don't draw the Lewis dot structure right. So this is all resting upon our artistic abilities to draw the structure correctly and run it through the flow chart and get the character table. So we have all these different types. This is sort of a photo of your handout. But we can also look at them. Let's turn to, well, just on the front page, D2H. D2H. Look how many symmetry elements we have. So we've got, C2s around the Z-axis, Y-axis, X-axis. We have an inversion center. We have 3 planes of symmetry. We have lots of symmetry operations in a C2 or D2H character table. Flip the page. Look at benzene down here at the bottom. This is D6H. So this is for benzene. Look how symmetric that molecule is. It's got a C6. When it says 2 C6s, that means a C6 sort of 1 notch clockwise, 1 notch counterclockwise, 1/6 of a turn. It's got some C3s, so it could go 2 clicks to the right or 2 clicks to the left of a C6 or 1/3 of a turn. It's got a bunch of C2s. There's 6 different C2s perpendicular to the C3 or C6. It's got an inversion center. It's got these improper rotations, a sigma H plane and 6 sigma vertical or sigma D planes. So this has all those different symmetry elements. And then look at all the rows it has too, all of these different Millikan notations. There's a lot of things that these symmetry rows capture other than the X, Y, and Z polarized light or the Raman modes or the rotational things. There's some of these symmetries that don't have any kind of spectroscopic connection to it. So a lot of the motions in the molecule or molecular orbitals in the molecule will not interact with light at all. Like if we get a motion that's say B1U or B2U down here, it's not going to interact with X or Y or Z polarized light. It's on a row that doesn't have one of those. And so there's a lot of what we would call dark modes, ones that aren't allowed in the Raman or allowed in the infrared in benzene, and that's because it's a symmetric molecule. On the back page, we have the direct product tables. Now these have been summarized. The direct product tables on the back. Okay, these have been summarized, and notice that some of these have multiple point groups that they apply to, like tetrahedral or octahedral, the A1, A2, E, and T1 and T2. The reason that they can apply to both is because they pulled the G and U rules out. So up here in the top left-hand corner is the G and U rules. So in an octahedral point group, you have A1G, A2G, A1U, A2U, and so on. But the A1 and the A2 and the A3, whatever rules, are the same as they are in the tetrahedral. But in the tetrahedral, we don't have G's and U's. So we can use the same direct product table for tetrahedral and octahedral, and then just add the G and U rules for the octahedral ones. Okay. So we can do some examples of that in the future. But for now, let's look more in these character tables. So we've found the Schoenflies notation where the point group is, this Millikan notation of the different rows in the character table, we have the symmetry elements across the top, and in the middle we have the characters. We're going to deal a lot with the characters today. And then we have these other, what they call basis sets, basis functions that where the x-axis or anything with x symmetry would show up. In this case, it would be on B1. Anything with y symmetry would be a B2 symmetry. Rotations on here, we have the second order things for Raman. So these are not really a part of the character table. They're just like cheat sheet. Okay, somebody's already gone through and done the work for these different combinations of X, Y, and Z and went ahead and put them in the character table just for your benefit. Okay. The character table is really just this piece in blue. And so this character table is a compilation of all the different symmetry representations that we have in the molecule. And we have two types. We have an irreducible representation, which means they're all linearly independent. And then we have a reducible representation, which is a sum of one or two or more rows in the character table. And so today we're going to learn how to take the reducible representation and decompose it. So that's the phrase here. We're going to take the reducible and decompose it into its irreducible representation. And we're going to do this for all of the vibrations and motions in the molecule. So a motion can rotate, it can vibrate, and it can translate. And so we should be able to operate on the molecule, and by operating through all the symmetry elements, we will get all of the possible motions of the molecule, or at least the symmetries of those motions. The goal is to find what row a particular motion is in, whether it's a translation or whether it's a vibration or a rotation. Because once we know the row of that motion, we can determine how it's going to interact with light. Because light is an oscillating electric field that's going to come in along the X, Y, or Z axis, or a scattering phenomenon of two photons that will interact with two axes, either the same, like X squared, or X times Y. So we need to know the rows of the various motions in our molecule before we can do the spectroscopic selection rule. There are some labels that we have. There's a scheme to this. So a label is an A if the character under rotation is a +1. And so you can see that over here. Let's look at the C2V character table. Where's my pen? Okay. Under C2V, the +1s here are labeled A, and the -1s here are labeled B. So that's the difference between the A and B labels. But these are still single dimension labels. The E operation has a 1, and so all the A's and B's have a dimension of 1, or I would say a degeneracy of 1. The two-dimensional rows are labeled E. And we talked about this last time. There's an E as a row, and there's also an E as a column. So I'm sorry about that, but anyway, that's what we've got. And these are two-dimensional. So look under the identity operator on the E row, it's 2. And these are going to be doubly degenerate. Oh, let's say doubly. Oh, my eraser's not working. Oh, boy. I'll say degeneracy equals 2. For E. Right there. There are some that have three-dimensional rows. So go to your character tables, and it's on, let's see. Yeah, on page 2, the back of the front page, page 2, look at the tetrahedral and octahedral character tables. So the tetrahedral is on the back of the front page. It's right here. Look at the T row. Where have you seen that? I think you might have seen it in inorganic when you're talking about the octahedral and tetrahedral complexes, and you had the T2G and the EGs, the d orbitals splitting into 3 and 2 pairs or groups. That's what you were labeling them. You were labeling those with the Millikan notation for an octahedral complex or a tetrahedral complex. Notice in an octahedral, so X, Y, and Z, that would be like the PX, PY, and PZ orbitals in an octahedral complex, or T1U. If you have 5 degenerate d orbitals and they split into 3 and 2, the 3 would be T1U in terms of the splitting of those. And then the no, T2G. See the X, Y, X, Z, and YZ? Those are the d orbitals that split out in an octahedral complex, and those are T2G orbitals. And then the EG would be the x squared minus y squared, and the 2dz squared minus x squared minus y squared. That would be the EG. Now looking at tetrahedral system, we have T2, no U or no G, because the tetrahedral molecule does not have an inversion center. And then look at the E. So it would be E and T2 in a tetrahedral complex for those d orbitals splitting, or the PX, PY, and PZ would be T2, or in the octahedral that'd be T1U. So you've been perhaps using these Millikan notations in other classes and just didn't know it necessarily. Okay. And then the G's and the U's are for Gerada and Ungerada. Now there are some 4D rows and 5D rows labeled G and H, but I don't have any of those on our little subset here, I don't think. Yeah. That would be like if you have like a, probably like a D5H or something with fivefold symmetry. Anyway. Okay, so then the G and U symmetry is under the inversion operation. So let's do this reducible representation. So what we're going to do is we're going to take the molecule, water, and we're going to look at all of the possible motions we can have for water by operating on it with the C2 and the two mirror planes. And so this is this reducible representation that we get from moving all of the atoms in water. So here's how we're going to do it. Here's our water, and I've drawn the X, Y, and Z coordinate system on each atom. And that'll become important here in a minute. But there's this equation out of Harrison Bertolucci's book, also out of Cotton's book on chemical application of group theory, and it's how we come up with this reducible representation character. So this R is for reducible right here, and this is chi is for character. So this chi is for character, okay? And we're going to go through this equation, and it's going to give us those characters after we operate on the molecule. And so the first one, so this is the number of atoms unmoved by the symmetry operation. Do y'all have that in your notes, or do you have blanks? You have it in there? Okay. And then this plus or minus 1, you have to pay attention to which one you're using, whether it's E or whether it's C2, etc. So it's a plus when you're using E and C rotations, and it's a minus for inversion or a sigma plane or an improper rotation. Okay? Is everybody clear when to use the plus or minus 1? And then we have the K and the N. So they're both equal to 1 for E and sigma and I. Okay. So let's look at this. Let's look at the character under E. So first of all, we have 3 atoms. And so when we do the E operation, what have we done to the atoms? Nothing, okay? So we have 3 unmoved atoms. So we start out with a 3 right here. 3 unmoved atoms. Is everybody cool with the 3? Okay. Then we have the plus. Why is it a plus? Because it's an E operation. Yes. And then for E and sigma and I, we have the K is 1 and the N is 1. We're not rotating it, so we don't know how far to rotate it because we're not rotating it at all. So we're just going to say E is 1. And K is the number of times you do that operation, and we're just doing it one time. So we have 1s here for the E, sigma, and I. So then we got to figure out our cosines. Okay? So we have the cosine of 2 pi. So let's just draw it out. So this is cosine. Starts out at 1, goes to minus 1, and comes back to 1. So it goes down and back up. That's one period of a cosine. Okay? Now where are all these pieces? So this is halfway across. This is 2 pi, right? So halfway across is pi. Okay, and this is pi over 2 where it crosses 0. So pi over 2, and then what is this one? 3 pi over 2? 3 pi over 2. Did I do that right? Yeah, okay. So we've got that. So these are our main features of our cosine. And so we're at 2 pi. So this is equal to plus 1. So this piece right here is plus 1. Is everybody fine with that? Then that plus 1 times 2. So we have 2 now. We're going to add another one. So that's 3. 3 times 3 is 9. We got there. Okay. So under E, the molecule has a character of 9 as a rotation, as a reducible representation. So all of the motions of this molecule are going to add up to 9. Now, does that make sense? Think about the molecule. How many degrees of freedom we have? Each atom has 3 degrees of freedom, X, Y, and Z. It can move in X, Y, and Z. So if we have 3 atoms, 3 times 3 is 9. So this reducible representation should be the sum of 9 rows in our character table, because we have a row associated with each motion in the molecule. Now we only have 4 rows, A1, A2, B1, and B2, so there's going to be a lot of repeats. But we will add up 9 rows to get this reducible representation that represents all the motions in the molecule. Is everybody cool with that? It's okay. So we got, so this, under E, we should get the total degrees of freedom for the molecule, which is 3n. Okay, let's do this now for C2. So for C2, n is equal to 2. Okay, we're only doing one rotation of that, so k is equal to 1. K is the number of times you do the rotation, so it's C2 to the k power, so it's just to the first power, so that's where k comes from. So we end up with pi over 2, so here, 2 pi over 2, so the 2's cancel, and you end up with pi. So now we're right here in terms of our cosine. So is everybody all right with the cosine equal minus 1? All right. So we have minus 1 times 2, so we have minus 2. So 1 minus 2 is a negative 1. And this was, okay, what about this guy? I didn't talk about that one. Why is that a 1? Pardon? Oxygen hasn't moved. So we did a rotation, and the oxygen's on the axis of rotation, and so the character under that rotation is 1. Or the piece, that piece NR is just 1. Okay, so we end up with minus 2 plus 1, which is minus 1 times 1, so we still have minus 1. So that's this reducible character here for C2. Yes? Because it's a C2. Yeah, so this is the N right here. Yeah. In our situation, yes. Yeah. So like even in benzene, we had a C6. There was 2 of them. It was a C6 plus like C6 to the first power, or C6 to the minus 1 power, or the opposite direction. So K would be minus 1 in that situation. Okay. But this is going to be symmetric in all of these cases, and so it ends up giving you the same character whether you do K minus 1 or K plus 1. But yeah, it's but it's going to either be 1 or minus 1. But in all our cases, it's going to be plus 1. Yes. Okay, very good. So on this C2 rotation, so this is the C2 axis on the molecule, and so if we do a C2, the 2 is how much you can take the full circle. You divide it by 2 and you get 180 degrees. And so then we can see the hydrogens will replace each other with a 180-degree rotation. So that's a C2. So in this case, for a C rotation, N is equal to 2. So let's do for a C2, N equals 2 and K equals 1. that make sense? For like a C6, N equals 6 and a K equals 1. Like for benzene, if we were doing benzene. It's always 1 in our situation. Yeah, it doesn't have to be, but in our situation it is. Yeah. You can look through the character table and let's see. In these situations, like look at C3V, just the third one down, C3V. You have that C3, like think of ammonia. You got the nitrogens and the hydrogens here. And a third of a turn will take this hydrogen and move it over to that one, right? But a minus third of a turn, a CK minus 1, would be moving it this way. Okay, so we have 2 different C3s because they have different results. We have a C3 to the first power, or we have a C3 to the minus power. Yeah. So I think we've got all the pieces now. The oxygen didn't move, so that's why this is a 1 here. Oxygen stayed put. Do y'all understand that phrase? That's a southern phrase. Stay put. Okay. Okay. Now let's do the next one. So sigma xz. So sigma xz. So the xz plane, you can see here the xz plane is this plane coming out of the board. So what atom didn't move? The oxygen again. The oxygen's right on the plane, and so the hydrogens swap places, and so we ignore them. The oxygen didn't move, so we have stayed put, and so he stayed put again. Okay. And then we've been told by definition n equals 1 and k equals 1. So this is k and n, they're both 1. Okay. So we have a cosine of 2 pi, which is plus 1, times 2. So we have plus 2 minus 1, which is now plus 1 times 1. So we get a plus 1. Did everybody follow that? I'm just speaking the math out loud. And so you can see that this minus 1 went here, and then this plus 1 goes here. Now this one's going to be interesting. This next one's a reflection, but it's 3 instead of 1. And that's because all 3 atoms stayed put. We did a reflection in the plane of the molecule. The hydrogens didn't move, the oxygen didn't move. So we still have a plus 1 for the cosine, which multiplied by 2 gives us plus 2. We subtract 1, so now we're down to plus 1. Multiplied by 3, we end up with 3 here. So that's our 4th character in our reducible representation. Now, all of these other big ones like benzene and so on are more tedious, but not more difficult. So we can show water, but this is what you would do with benzene or an octahedral complex and so on. So it's not hard, it's tedious. Do you know the difference? Yeah. If you don't know the difference, this class will teach it to you. Yes. So it's not hard, it's just tedious. But yeah, 4 examples on 1 page is enough. It gets complicated in terms of how to display it. So that's what we call a reducible representation. So when we talked about the character tables, they were irreducible representations in the character table. But a reducible representation is a sum of multiple rows. So now let's decompose this and get to the combinations of all those irreducible ones. Now there is a way to shortcut this that you may have learned if you covered this at a different school. If I rotate the atoms and the axes together, I ignore the atoms that moved. So I throw the hydrogens away, and I just look at the oxygen. Look at the top one first. Look at all the atoms and all the coordinate systems. Okay, if I do an E on that, how many individual axes remain the same? So like X, Y, Z on all 3 atoms. There were nine axes, and none of them changed. So the character under E is 9. What about the C2? So I've got this coordinate system like this, where this is X, this is Y, and out of the top of my head is Z, okay? And I rotate 180 degrees, okay? The top axis has not changed, but these two are minus ones. So I have -1, -1, +1. So I end up with -1 total. So I have -1 plus -1 plus +1, and I end up with -1 net. And so that's the character under C2. Okay, then if I have this situation on the reflection in this XZ plane, the hydrogens move, so I forget about them. The oxygen has 3 axes, the Z, the X, and the Y. And I reflect it in this plane, so now the Y is over here. So that's a -1. And I have a +1 and a +1 because those haven't moved. And so I add all 3 of those together and I get +1. So that's this one, this character under XZ. And then I've got all 3 atoms with these 3 axes, and I reflect them. And so now my x-axes are pointing back. So those 3 axes are -1. And then this is +1, +1, +1. And so I have 6 axes that didn't change, 3 axes that did. The net result is +3. So just counting up the axes that don't move, and if they change +1 or -1 is a shortcut to that. If you didn't understand the shortcut, watch the video again, pause it, do it by hand if you want, but this will always work. Okay, the shortcut can get confusing, especially on something like ammonia, where you're rotating a third of a turn. What do I get when I take an x-axis and rotate it 120 degrees? Is that a -1? Is that a +1? I don't know, you know. And so the axes don't really work when you have a third of a rotation. But they work great if you have 90-degree rotation or 180-degree rotation. So that's why I don't really emphasize that way of doing it. I just do the brute force cosine equation to get the characters for the motions of the molecule. Okay, so here's our reducible representation down here, and we have all our irreducible representations up above. And so let's break this apart. So we have the number of symmetry elements is called the classes, and there's 4 of them. Okay, and then each of those classes has a certain number of members. And so you can see, let's look at C3V again. You see under that 2C3, there's 2 of those. So GI for that would be 2. The sigma planes, there's 3 of those. So the G of I would be 3 for that. Okay. But in water, every one of our symmetry elements just has a single member in each group. Okay. Do you see that under the 3 sigma V's or the 2 C3s on the C3V character table? Yeah. So those are the GIs, the number of members in each group. And then the order of the group is the sum of all of those GIs. And so for C3V, we have 1 for E, another 2 for the C3s, and 3 for the sigma V. So the order of that group would be 6. You add up all of those numbers and it would be 6. Let's go over here to D2D. Let's add up all of those. 1 for the E, 2 S4s, so that we're 3. We have a C2, so that's 4. 5, 6, 7, 8. So the order of that group is 8. And so then the number of irreducible representations matches the numbers of classes, so K. So the tables are square, in other words. So this reducible representation is what I said earlier. It's equal to 9 of these rows. So there's going to be a certain number of A1 rows, a certain number of A2s, a certain number of B1s, and a certain number of B2s. So how do we solve for these little coefficients? That's what we want to know. We want to know how many A1s there are, how many B1s there are, etc. So there's another equation for that. This is the equation for that. Okay? So this little A for each of those reducible representations is 1 over G for that particular, 1 over the G, the order of the group here. And the sum of this 3 of these numbers times each other. So let's learn by doing. So this coefficient, the number of A1 rows we have, is 1 over 4, because that's G. So there's four column numbers. And then we have this E, this G up here, the number of members in the E group, times the reducible representation, and then times the character on the A1 row. So we do it one row at a time. So all three of these numbers times each other, added to the next three numbers, added to the next three numbers, added to the next three numbers. So we've got 9 minus 1 is 8, plus 1 is 9 again, plus 3 more, okay, 10, 11, 12. So we have 12 divided by 4 is equal to 3. So again, it's not hard, but it's tedious. You got to do all of these little rows times each other. But this tells us that there are 3 A1s in this sum. It's going to be 9 rows total, and 3 of those rows are A1 in this total. Okay, let's do A2. Okay, so we now know that that's 3. My eraser, I wish it would work. Yeah, phooey. Let's see if I can do this. Anyway, can't erase. Anyway, that's a 3. So now let's do A2. So now I've color-coded it yellow. You see the yellow ones here? Everything's the same except that number. Instead of the green numbers, I have the yellow numbers, but everything else is the same. So I end up with 9 again, minus 1, so we're down to 8, minus another one, so we're down to 7, minus 3 more, so we're down to 4. 4 divided by 4 is 1. So we only have one A2 row in our sum of all of our motions of our molecule. Okay, let's do this one, B1. So now this is this row, it's purple, you just can't really see it very well. Same everything, except we've got the purple row. So we're at 9. Okay, minus 1 and minus 1 cancel out, so that's going to add. So now we're up to 10. Then we're at 11. And then 11 minus 3. What is that back down to? 8? Yeah, so it drops down to 8. 8 divided by 4 is equal to 2. Now there's a nice little trick. If I did my math wrong and say I couldn't subtract 3 from whatever I was trying, 11, and I thought it was 9. When I divide 9 by 4, I don't get an integer. And so I know I've screwed something up. So it's going to work out to where when it's going to be a multiple of 4. So when you divide by 4, you should get an integer. If you don't get an integer, you've messed up something. You've used the wrong row. You've done something wrong. Okay, so that's a nice way to check your work. So I end up with 2 of those B1s. And then the last one is the B2. So now we're using this last row here. So I have 9, add again 10, subtract 1 back to 9, add 3 more, so we're up to 12. 12 divided by 4 is 3, and so we have 3 B2s. Okay. So now I know that those are the 9 combinations of irreducible representations that add up to the reducible representation. I have 3 A1s and so on. Now, what are those? Those are all the motions of the molecule. So the molecule can do 9 things. So what are those 9 things? Well, 3 of those are translations, okay? The molecule as a whole can move in the X direction. It can move in the Y direction, it can move in the Z direction. And the Z direction is an A1 direction. And an X motion is B1 and a Y motion is B2. So we could subtract out one of the A1s, because that's translation. We could subtract out one of the B1s, because that's translation in X, and B2 is translation in Y. Okay? It could also rotate. So if I'm rotating around the Z axis, that has A2 symmetry, and that's my one A2 that I have. So that A2 is a rotation, not a vibration, not a translation. And then whatever's left, think about those phrases, whatever's left is a vibration. So even benzene with 30 vibrational modes, so let's come up with that. We have 3 and we have 12 atoms, times 3 is 36. So benzene can do 36 things, but it can still only do 3 translations. So it can move as a whole in the X, Y, and Z direction. Benzene, even though it's a big molecule, can rotate around Z, around X, around Y. It can only do 3 rotations. So 6 of those 36 motions are translations and rotations. So we take them out. And all that's left, everything that's left, is a vibration. So this is how we determine how many vibrations a molecule has. It's 3n minus 6. So this is 3n minus 6. This right here is 3n. So we've taken the total number of degrees of freedom in the molecule and we've subtracted out the 3 translations and the 3 rotations. Now there's one caveat. If it's a linear molecule, we only have 2 rotations, but we can talk about that later. Okay, but 3n minus 6 vibrations for a nonlinear molecule. And you see why we do it by difference, because it could be 3n. N could be anything. It could be DNA. DNA molecule somehow in space, blow off a comet. There it is, it could still only translate three ways. It can still only rotate 3 ways, but it can vibrate 3n minus 6 ways. Yeah. So here's water, and here's all of the motions in water. So there's 3n total degrees of freedom. There's 3 translations. Do you understand the arrows? Look at the arrows compared to the X, Y, and Z axes. So these 3 arrows are diagonal, like that X axis. So that's really meant to show it's coming out at you. And it can move in the Y direction, or it can move in the Z direction. And that's it. That's all water can do in terms of translation. Then rotation. I've drawn this stick trying to come out. It looks like it's rotating this way. Then this one is rotating this way, and this one's rotating this way. That's all you can do. There's 3 axes. You can rotate around all 3. So if there's 3 rotations. And then whatever's left, they're the vibrations. So we have 3n minus 6, which is the 3 translations, 3 rotations, and then that's what we have for the vibrations. So these are the after we did the irreducible representations, we reduced or decomposed our reducible representation. We know we have 2 A1s and a B2. That was from that previous slide. I didn't really point that out. Right here, this column. So after we've subtracted one of our A's, we have 2 A's left over, A1s. See, we have 3 here, and we've used 1 up for the translation, and so we have 2 left for the vibrations. We used this one completely, so it's gone, okay? And then the 2 B1s, we used it there and there, so there's none left, right? So we're out of B2s, or B1s, sorry, we're out of B1s. So we're done with that. And then for the 3 B2s, we used 1 here, we used 1 here, so there's only 1 left. So we have a vibration that is B2. Yes. Three translations, but we can only have 2 rotations. And it's because if this is a linear molecule, there's no mass off the axis, and so we can't define that as a rotation. We would never be able to detect it. There's no moment of inertia. So there's no resistance to rotation. So there's no way to sort of measure it. There's no way to define it. How would you define it since there's nothing off axis? If you're going to try to define rotation by an angle, what are you going to tack that angle to? There's nothing off the axis. So there's nothing about the molecule, this linear molecule, that could even be used to determine a rotation. So it's just really not definable. So we say it's not defined. So we can certainly do a rotation like this. That would be around the x-axis. And we could do a rotation around this, around the y-axis. But around the z-axis, we can't even define it. So we only have 2 rotations for a linear molecule, no matter how long. Nonlinear? Yeah, nonlinear is 3, because you can rotate around x, y, and z. Yeah. And then translation's always 3, always, no matter how big the molecule. Earth has 3 translations for the planet Earth. There's a lot of atoms. But in terms of vibrations, it's you want to know how many vibrations Earth has? Count up the number of atoms and subtract 3 translations and 3 rotations, and the rest is vibrations. Yes, it's a lot of vibrations. Yeah. And so then let's. What's going on? Okay, here we go. That's kind of glitchy. Oh, I started doing ammonia. Sorry, let's go back. We're kind of out of time. Yeah, so here's the water. So we end up with these last three here. These are the vibrations. And this has Z symmetry. So we can look up Z symmetry and determine that it's A1. How do I figure that out? We'll do that next time. Okay? And how do I figure out this is Z symmetry? We'll do that next time. And this one is Y symmetry. We'll do that next time. But here's our two A1s, and here's our B2. Okay. Now, I in the notes, you have an example of ammonia going through. We're out of time, but let me just run through the slides so it'll be in the video. So we do the same thing for E. We have 4 atoms unmoved. Do the cosine business, you get 12. For the C3, notice N equals 3 here. Okay. So it's 2 pi over 3. And so that's going to end up being a cosine of 0.5. Yeah, I might have to use your calculator for that one. Okay. Times 2 gives us 1 plus 1. That's a minus a half. Times 2 is going to be minus 1 plus 1. It ends up being 0. So that's going to be 0 there. And then this one is going to give us a character of 2. So we have that reducible representation for ammonia. And then we can go through and do the decomposition. So we can work through our equation with our 3 rows. We get a 3 for A1. We get a 1 for A2. And we get a 4 for E. So this is the full thing set to ammonia, where you have a third of a rotation, and you got to take a cosine of 2 pi over 3, coming up with minus 1/2 for that. Okay. So of these, we have 3 translations. We have 3 rotations. And so then the rest is 6 vibrations. And those 6 vibrations are going to be 2 A1 vibrations, because we only used up 1 for the Z. So we have 2 more left over from this 3. We've used up our A2 for rotation around Z. And then they have 4 E's. We used up 1 here and 1 there, and we have 2 left over. Now this is strange because we have 6 vibrations, but it looks like we only have 4 things here. But these are doubly degenerate, right? So there's a rotation, or there's a vibration in the X direction and a Y direction under 1E, and they count as 2 different vibrations, but only 1 symmetry for that. So that's where we end up with looking like we only have 4 vibrations, but these count twice. Okay. So that's all in the video. I would say you might want to go back through it, because as I talk quickly and you're trying to write your notes, you probably miss some things. So.